Picture this. You're standing on the stage of one of the biggest game shows in America. The lights are blinding, the audience is holding their breath, and in front of you are 3 closed doors. Behind one of them, a brand new Tesla, the latest model, 0 miles. Behind the other 2, goats. You point to door number 1. The host, a man who knows exactly where the car is, doesn't open your door. Instead, he walks over to door number 3 and swings it open. A goat stares back at you. He smiles. He looks you in the eye, and he asks, "Would you like to switch to door number 2? Now, what do? Most people think, there are 2 doors left, it's 50-50, switching doesn't matter, and most people would be wrong. Here's the truth. If you don't switch, your odds of winning are 33%. If you do switch, your odds jump to 66%, double. And before you click away thinking I'm making this up, this problem once triggered over 10,000 angry letters sent to a single magazine. Letters from PhDs, from math professors, from people who dedicated their lives to numbers. They were all wrong. Welcome to the Monty Hall Problem, the paradox that broke the internet before the internet even existed. Let's go back to 1990. Marilyn Savant, at the time listed in the Guinness Book of World Records for the highest recorded IQ in history, wrote a column in Parade magazine. A reader asked her about this exact problem. She gave her answer: you should switch doors. The backlash was immediate and savage. More than 10,000 letters flooded the magazine. Thousands of them were from professors, statisticians, scientists. One letter from a PhD at the University of Florida read, "You are wrong. Stick with your original choice." A professor from George Mason University wrote, "You made an error. If this continues, it will be an embarrassment." One letter, I'm not making this up, literally said, "Maybe women look at math problems differently than men." Yeah, it got ugly. But here's the twist. Marilyn was right. Every single one of those professors was wrong. Some of them, to their enormous credit, later ran computer simulations, confirmed the answer, and wrote apology letters back to the magazine. A Stanford statistician said it was one of the most valuable lessons in probability he'd ever encountered. So how is it possible that an answer this counterintuitive is correct? Why does our brain refuse to believe it? Okay, let's break this down. I promise this won't feel like a lecture. When you first picked door number 1, what are the odds you picked the car? 1 in 3, 33%, which means the odds the car is behind one of the other doors. 2 in 3, 67%. Simple so far. Now here's the key insight that most people completely miss. When Monty opens a losing door, he is not acting randomly. He can't open your door. He won't open the car door. He always opens a goat. That means his action carries information. Real, valuable, probability-shifting information. Let's walk through every possible scenario. Scenario 1. You picked the car right away. Lucky you. 1 in 3 chance. Monty opens any goat door. You switch. You lose. Scenario 2. You picked goat A. Monty has to open the door with goat B. It's the only one he can. You switch. You win the car. Scenario 3. You picked goat B. Monty has to open the door with goat A. You switch. You win the car. Count it up. 3 scenarios. Switching wins in 2 of them. The reason we think it's 50-50 is that we reset the math when a door is eliminated. We think 2 doors. Fresh start. Equal odds. But it's not a fresh start. Your original door still carries the weight of a 1 in 3 pick. The other door now absorbs the remaining 2 in 3 probability. Your door didn't get better. The other door got much better. Still not convinced? Try this. Forget 3 doors. Imagine 100 doors. The car is behind one of them. You pick door number 1. Your odds? 1%. Now Monty, who knows everything, opens 98 other doors one by one. All goats. He leaves only two doors closed, yours and door number 64. He turns to you. Switch? Think about what just happened. Your door was picked blindly from 100 options. The odds were terrible. But door 64 survived 98 rounds of deliberate, informed elimination. It didn't survive by luck. It survived because Monty couldn't eliminate it. Would you switch? Of course you would. You'd run to door 64. The three-door problem works the exact same way. The math is identical. The only difference is that the gap between staying and switching is less dramatic. 33% versus 67% instead of 1% versus 99%. The structure is the same. The logic is the same. The answer is the same. Switch. Here's what I find fascinating about this problem. It's not just a math puzzle. It's a window into a very specific cognitive trap, something psychologists call choice supportive bias. Once we make a decision, our brain starts defending it. We look for reasons we were right. We resist information that says we should change. The Monty Hall problem forces that bias into the open because the math is simple enough to verify. And yet our gut still screams 50-50 even after we've seen the proof. And it shows up everywhere. In investing, people hold losing stocks because they believe in their original thesis. In relationships. In careers. We stay on paths that aren't working because switching feels like admitting we were wrong, like weakness. But the math says something different. Switching, when you have new, reliable information, isn't weakness, it's optimization. It's the rational move. The goat behind door 3 is information. It changes your odds whether you feel it or not. The Monty Hall problem has been around for decades. It's been debated in math departments, coded into simulations, argued on Reddit threads at 3 in the morning. And every single time, the answer is the same. Switch. Not because of gut feeling, not because of luck, because the math, once you really see it, is inevitable. So the next time life opens a door and shows you a goat, pay attention. That's new information. Adjust. Adapt. Switch if it makes sense. The car might be closer than you think. If you made it this far, drop a comment telling me, what was your gut answer before I explained it? Stay or switch? I want to know. And if you want more videos on the paradoxes and mental models that quietly shape how we think, subscribe. We're just getting started.